All right. So in case of DC generator, the nature of EMF induced in armature is AC, right? So you know, I want you to understand the fact that the dynamically induced EMF is always sinusoidal in nature, right? Right in single phase AC circuits you have seen. Let's say, okay, let us assume a pair of poles, a north pole and south, right? Let us also assume the flux orientation, something of this kind, okay, this kind. And if we place a conductor in this particular magnetic field, hello, sorry, class, sir. Okay. Now, here field system is stationary and conductor is allowed to move. Now, let's say if the conductor moves in direction 1, that is perpendicular to magnetic flux lines, the induced EMF E is maximum. Induced EMF E is maximum. And you can write an expression something like BL into V, where V is equal to velocity of the conductor and L is equal to active length of conductor, active length in meters, and B is the flux density, which is expressed in Tesla. Okay. On the other hand, if the conductor were to move in direction 2, so in direction 2, the tendency of motion is parallel, right? Parallel to flux lines. So when the conductor tends to move parallel to flux lines, then there will be no change in flux. If there is no change in flux, you can say that d phi by dt is 0. So induced EMF is proportional to d phi by dt, right? As per Faraday's law. So induced EMF is 0. So whenever the conductor moves parallel to flux lines, the rate of change of flux is 0. Therefore, EMF induced will be 0. On the other hand, if the conductor is inclined at an angle theta with respect to plane of flux, let's say this is the angle theta. If the conductor is inclined at an angle theta with respect to plane of flux, then the motion of the conductor can be resolved into two components, right? Horizontal component and vertical component. So the component along direction 2 is nothing but V cos theta. And the component along direction 1 is V sin theta. So what happens over here is that the component which is projected along direction 2 doesn't take part in EMF induction, right? That's because this particular component is parallel to flux lines. We have already seen that whenever the tendency of motion is in parallel to flux lines, the rate of change of flux is 0. So out of the two components, the component of the velocity, which is perpendicular to the plane of flux, takes part in EMF induction. And therefore, the induced EMF, when the conductor is inclined at an angle theta, can be given as E is equal to EM sin theta. Okay, which is actually E is equal to B into L, that is flux density into active length, into the velocity component, that is V into sin theta. We already know that BLV is a constant which refers to yield. Hence, this BLV can be replaced with yield. So, the setup in which we have had a constant magnetic field but a rotating conductor, which is similar to your DC generator setup, right? In DC generator, on the stator, we have magnetic flux, or sorry, magnetic poles, which carries magnetic flux, and we have a rotating armature. So, whenever a conductor is rotated in a constant magnetic field, the induced EMF always follows the sinusoidal law, that is E is equal to Em sin omega t. So that's the reason in a DC generator, the nature of induced EMF in the armature is always AC. But our objective is to produce direct current electricity. That is the reason what we do is the alternating current in a DC generator is made to flow through the commutator. So this process is called as commutation. By a process called commutation, bidirectional electricity can be converted into unidirectional electricity. So voltage which is coming out of the commutator is direct current or DC. On the other hand, the voltage which is present in the armature is always AC. Okay, you have to be very clear about it. Okay. All right, so that's about the working principle of DC generator. Okay. This is the working principle of DC generator. And direction of induced EMF or induced current can be given using Fleming's right hand rule, FRH. Fleming right hand rule. As per Fleming right hand rule, if we stretch the first three fingers of the right hand in such a way that the fingers are mutually perpendicular to each other. Mutually perpendicular to each other in the sense the angle between the respective fingers should be 90 degrees. Say for example, between my forefinger and thumb, I have 90-degree angle. Similarly, between my central finger and the forefinger, I have 90-degree angle. That is what is called as mutually perpendicular to each other. Okay, let's say this is your thumb. And the forefinger and sorry. Okay. This is your forefinger. Okay, and this is your central finger. And this is your thumb. Okay, so that I've highlighted a few letters intentionally. Okay, so M stands for motion. All right, that's the reason I have highlighted term M, and F stands for field or flux. Field or flux, it's one and the same. And C stands for current. Current, quite often we get confused because you have to by heart the fingers, right? So you don't have to by heart the fingers. Thumb M for motion, forefinger F for flux, and C refers to central finger, and C refers to current. Okay. So if you outstretch the first three fingers of your right hand in such a way that they are mutually perpendicular to each other, and if thumb is pointed in the direction of motion, and forefinger is pointed in the direction of field, then the central finger will give the direction of induced current. That is about Fleming's right hand rule. Okay. So Fleming's right hand rule is applicable to generator. Okay. On the other hand, Fleming's left hand rule is applicable to motor. Okay. So how exactly you apply Fleming's right hand rule and left hand rule? Let me tell you sometime later. All right. Fine. So that's about the working principle of DC generator and the explanation regarding the Fleming's rules. All right. Fine. Next, let us take up a topic called EMF induced in DC generator. Okay, rather expression for EMF induced in DC generator. Okay, class strength is very poor. It is just 16, which is very disappointing. Okay, I don't know what are you thinking of yourself. You are in electrical engineering branch and you don't want to attend the electrical engineering class. Very unacceptable situation. So if you don't understand DC generators, what will you understand in a higher semester? I don't know. Right? You have chosen this branch because you want to be an electrical engineer, right? You probably want to work with EV industry, etc., etc. Many students are simply exploiting the COVID situation and simply they don't want to attend the class. If you don't attend the class, how will you understand the machine working, or how will you understand the fundamental, preliminaries of DC machines? So what you will do, you will tend to by heart this stuff. By hearting will not serve the purpose, right? So very disappointing. Okay, fine. So expression for induced EMF in DC generator. All right. Now to deduce an expression for an induced EMF in a DC generator, let us start by defining certain machine constants. All right. So let us define. Let's say P. P is equal to number of poles. Say phi. Phi is equal to flux per pole, expressed in Webers. All right. Let us say N is equal to speed of rotor, expressed in revolution per minute, RPM. And also, let us say A is equal to number of parallel paths. Okay, I will come to it, number of parallel paths. Though in basic electrical engineering, we are not going to do detailed assessment of, a parallel path, lap and wave winding, but it's okay. To some extent, I'll be able to, explain. Okay, as of now, let's take A is equal to number of parallel paths. You can just think of this keyword, parallel paths. So parallel paths refers to, the distribution of conductors in different paths. Paths could be 2 or more. Okay, all right. And then let us also define Z is equal to number of conductors. Number of conductors. Okay. So what we have done so far, we have defined certain machine constants: poles, flux, speed, parallel paths, and number of conductors. Okay. Now, the EMF expression is quite similar to the alternator. Only the difference is that your DC generator has commutator segment. Okay, that's the only difference. Okay, yeah, of course, in your DC generator, field and conductor systems are interchanged. Okay. So let's start with, in one revolution of the rotor, the flux cut by the conductor in one revolution of the rotor, that means to say, here you will start and here you will stop, right? So this is called as one revolution. In one revolution of the rotor, the flux cut by the conductor is taken as d phi, which is equal to d phi. Okay, that's because total number of poles are p and flux per pole is equal to phi. So total flux cut by the conductors in one revolution is p into phi. Okay. Next, time taken to complete one revolution is something like this. So n revolutions gets completed in 1 minute, right? Because revolutions per minute. Or you can say n revolutions are getting completed in 60 seconds. So what is the time taken to complete one revolution? What is the time taken? So basically, that time can be taken as dt, which is small time, small change in time. Okay. So that is actually 60 by n. Then, as per Faraday's law of electromagnetic induction, the EMF induced in one conductor, okay, let's say E is equal to d phi by dt. Okay, because one conductor means n is equal to 1. So d phi by dt. What is d phi? D phi is d phi. And what is dt? Dt is 60 by n. Or you can say that P phi n divided by 60 volts. So that is the induced EMF in one single conductor. Okay. However, in case of DC generator, you can write, in case of DC generator or DC machine, the conductors are placed in parallel paths. The conductors are basically placed in parallel paths. So normally, and which can be taken as Z by A, where Z is the number of conductors and A is the number of parallel paths. Okay. So here itself, let me tell you what you mean by parallel paths. Now, you have two types of windings in DC machine. Wave winding . In case of wave winding, the conductors are kept in two parallel paths. Always two. This is positive terminal and this is negative terminal. Why positive, negative? Because it's a DC machine. All right. So for a wave winding, the conductors are always kept in two parallel paths. So you can say A is equal to 2, first and second. So if you have, let's say, total conductors, Okay, let's say you have total conductors as 200. Then 100 conductors are placed in the upper part, and the remaining 100 conductors are placed in the lower part. So this is the meaning of Z by A. So how many conductors you are going to distribute in the parallel paths? Okay, this is for wave winding. So wave winding, your A value is always 2. Okay. On the other hand, in case of lap winding, here your number of parallel paths is equal to P. Number of parallel paths A is equal to P. That means to say, if your machine is consisting of 4 poles, then you are going to have 4 parallel paths, so on and so forth. So let's say 4. Then this particular machine is going to have 4 parallel paths. Third one and the fourth one. Plus and minus. Okay, so this is what you can visualize the meaning of parallel paths. Now, say for example, again, let us consider Z is equal to 200. So we have a total of 200 conductors, and let us say we are considering a lap winding. So in case of lap winding, you get parallel paths is equal to poles, and we have assumed, say, 4 pole machine. So 4 divided by 200 basically we are supposed to do. So how many conductors in each parallel path you will get? You will get about 50 conductors. So in case of lap winding, the distribution of conductors would have been 50 each in each of the parallel paths. Okay. Now, this is the understanding. All right. So taking the parallel paths into consideration, you can say that. Okay, I'll continue here. The induced EMF in Z by A parallel paths, the induced EMF in Z by A parallel paths is given as E is equal to, okay, you got P phi N divided by 60 into Z by A. P phi N divided by 60 into Z by A. So this is the expression for induced EMF. All right. So E is equal to phi Z N P divided by 60A is basically the expression for induced EMF. Okay. Now let us consider the special cases. You have 2 types of windings, right? Wave winding and lap winding. So the same expression can be extended to lap wound machine as well as wave wound machine. So for a wave wound machine, let's say wave wound generator. Okay. For a wave wound generator, what do you get? A as A is equal to 2. If A is equal to 2, you get E is equal to P phi N into Z divided by 60 into 2, that is 120. On the other hand, if you consider a lap wound machine, A is equal to P, and due to which E is equal to P phi N into Z divided by 60 into A. What is A? A is equal to P. So P gets cancelled. So you will get E is equal to phi Z N divided by 60. Divided by 60. Okay. So two different armature windings will give kind of two different EMF equations. Okay. So based on the type of DC generator, you can end up in producing more voltage or less voltage. So normally what happens is that in case of wave wound machine, okay, E is more. That is, if at all you want to produce high voltage, you can go for a wave wound generator. On the other hand, if you want to go for if you want to produce low voltage but high current, you can go for lap. So this is for high current, high I, and low V. Okay, it is suitable for low voltage, high current application, and wave winding is suitable for high voltage, low current application. So voltage fact you can appreciate from the equation. Current, how will I understand? I'm saying this is meant for low current applications. Quite simple, right? If you look at wave winding, how many parallel paths? Only two parallel paths you have. Let's say, for example, you have an incoming current of 100 amperes. So each of the two parallel paths would have received 50 amperes and 50 amperes. So that means to say the diversion path is only due to which the high current can flow. So you should see to that it is not subjected for high currents because you cannot divide the current into multiple parallel paths. Now, if you consider lap winding and if you consider the main current as 100 amperes, so this 100 amperes now can be safely distributed into four parts. Right? So each part becomes 25 amperes. So each parallel path is receiving about 25 amperes of current. Okay, let me write here. If I have 100 amperes of incoming current, upper half takes 50 amperes and the lower half takes 50 amperes. On the other hand, in lap wound machine, if I say 100 amperes of incoming current, then each of the parallel path would be receiving 25 amperes of current. So a lap wound machine EMF equation. All right. So you have two types of generators for two different applications: high voltage application and low voltage application, or you can say high current application or low current application. Okay. So this is the induced EMF. So in the induced EMF, what you have to do is you have to define the machine constant and define the EMF induced in one conductor. And then you can say that induced EMF in Z by A parallel paths is so and so. Okay, and for lap wound you will get this, and for wave wound you will get something of this kind. Okay, you don't have to show this. This I have shown for your understanding purpose. Okay, this you did not include. So that concludes the expression for induced EMF in a DC generator. All right. Once you are done with this, we can take up the next topic in DC generator. Okay, you can write down types of DC generator. Types of DC generator. Types of DC generators. DC generators, or rather DC machines, are classified. Okay, are classified on the basis of field excitation. On the basis of field excitation. Okay. What do you mean by field excitation? What do you mean by excitation? Excitation means, making a particular device to act, or making a particular device to, activate. So how would you activate the field winding? So that itself is called as field excitation. Now, field excitation can be of two types: self-excitation and separate excitation. Yeah, self-excitation and separate excitation. Self-excitation and separately excitation. Now, separate excitation means separate DC source is connected to field system. In the beginning, I said, in case of practical DC generators, we use electromagnets, right? So we use electromagnets. When you say electromagnets requires electricity to produce electromagnetic field, right? So if you connect a separate DC source to the field system, the corresponding generator is called as separately excited DC generator. DC generator. On the other hand, if let's say suppose we don't connect any external DC power supply to the field system, okay, then it is called as self-excitation. So if no external DC source is used to excite the field winding, we would say the respective generator as self-excited DC generator. Self-excited DC generator, and this is separately excited DC generator. A separately excited DC generator requires separate DC source, and a self-excited DC generator requires no DC source. Okay. So this is the first level of classification. Okay. In self-excitation, so in self-excited DC generator, there are different types. You have series generator, parallel generator, and compound generator. Compound generator. Okay, 3 types. Okay, there's no 4th type. It's a 3 classification. Okay. And in case of separately excited, there is no further classification. We have only 1 type of generator. Okay. So first, let us look at the separately excited DC generator. So definition of excitation is nothing but process of connecting or process of energizing the field system. Look, as simple as that. Process of energizing the field system is called as excitation. So first, let us consider a separately excited DC generator. So from here onwards, we will be drawing something known as equivalent circuit. Equivalent circuit. Equivalent circuit is nothing but it's a substitute circuit for the actual machine, because actual machine is pretty difficult to draw, right? You have to draw stator, then field system, rotor, conductors, commutator, etc., etc. So we don't do it in we don't draw such a diagram for analysis sake. For analysis sake, we always draw the equivalent circuit, right? See, diode, you have studied in basic electronics. So diode you could replace with an equivalent circuit. Forward bias it conducts, reverse bias it doesn't conduct, right? So based on that logic, you could draw an equivalent circuit for diode. In a similar sense, you can also draw an equivalent circuit for DC generator. Now, your DC generator or DC motor, in other words, a DC machine, is consisting of 2 major parts, stator part and rotor part. Stator is consisting of field system and rotor is consisting of conductor system. That's all you are supposed to draw. You are supposed to draw the field system as well as the rotor system. Now let's come to the separately excited DC generator. As I said in the beginning, in case of separately excited DC generator, the field system is connected to an external DC power supply. Alright, so field system can be represented with the help of winding. This is your winding. Hello, class 11, sir. Okay, so this is your field system. Normally, field is represented with F, double F terminology. F is assumed as the terminal which is getting connected to the positive polarity of the supply, and double F is connected to the negative polarity of the supply. Okay, so similarly, F is connected to positive terminal of DC source, and double F is connected to negative terminal of DC source. So this is your DC supply. As expected, right? Separate excitation. It needs a separate DC power source. Okay. And the resistance of field winding, let us call it as RF. So RF simply refers to resistance of the field winding. Okay, and this DC supply can be given a name, something like VF is the voltage applied across the field winding, and the current that flows through the field can be taken as IF. Okay, so this is your field system. Field system. So you're done with the field system. Now you are supposed to draw the armature system. Okay, so you can look closely. So armature is basically circular in nature and it is rotating type, right? So that's the reason, we draw small symbol, something like this. Okay. A circular object we will draw. Okay. Now, the circular object is your generator. For generator, we write G, and for a motor, we will write M. Okay. And the two small rectangular boxes shown above and below this generator refers to brushes, right? Carbon brush, do you recall? So carbon brushes are basically mounted on the commutator to collect electrical current from the rotating part of the machine, and you need to supply this current to external circuit. So the top brush is taken as A, and the bottom brush is taken as WA. So same subscript topology we are going to use. Single letters refers to positive polarity. Double letter notification, okay, or representation is related to negative polarity. All right. So that is your armature representation. Now this armature is made up of what? Conductors or windings, either lap winding or wave winding. So this armature is made up of considerable amount of copper wire, right? So copper will possess finite resistance. So we can also show the resistance of armature with a resistance value. And let us call this resistance as RA. So RA refers to the resistance of the armature or resistance of the armature winding. And the terminals of the generator, it is connected to an electrical load. So this is your load. It is your load. Okay, I can write electrical load, because when you say load, you shouldn't get confused with mechanical load. So it is connected to electrical load. Okay, and the EMF which is present across the terminals of the generator, that is across A and WA, is called as EG. EG. That is generated EMF. And EG you have already derived, right? So EG, or simply E, is nothing but phi Z NP divided by 68. And the current which is flowing through the armature can be taken as IA. And the current which is flowing through the load can be taken as IL. Okay. And the voltage across the load, let us take it as VT. And VT refers to terminal voltage. Okay. VT with a given polarity. And this is called as the terminal voltage. Okay. Now, when the armature current IA flows through the armature resistance RA, there will be a small armature drop, right? Voltage drop. So that voltage drop, we can take IA into RA. Okay. And in the usual sense, you can put the polarity, right? So this is positive and this is negative. So that completes the equivalent circuit of separately excited DC generator. You have marked different currents and voltage. Okay. IA stands for armature current. IL stands for load current. VT stands for terminal voltage. EG stands for the EMF generated in the armature. Okay. RA refers to armature resistance. RF refers to the field resistance. All right. Next. Observation. Observation. So, if you look at the equivalent circuit, okay, what do you observe? Let's say, pay your attention to the flow of current in the armature circuit. So, if you look at the equivalent circuit, you can see that the armature current itself, flows into the electrical load. So IA is equal to IL for a separately excited DC generator. So from observation, you can say that the armature current IA is equal to load current IL. Okay, fine. So that is your one of the observation. And you can also see in the armature circuit that different voltages are present. You have a voltage across the armature terminal, a drop across the resistance RE, and a terminal voltage across the load. So what you can do is you can apply KVL, let's say in the given direction, let's say in the clockwise direction. So when you apply KVL, you will be able to relate the generated EMF EG with the terminal voltage VT. Okay, so let's apply KVL. So in the anti-clockwise direction, sorry, clockwise direction. Yeah, clockwise direction. So what do you get? -2 plus EG plus 2 minus IARA and plus 2 minus VT is equal to 0. Okay, so this is the most ideal expression what we have considered. However, a practical DC generator will have we will have to consider two practical phenomena over there. Now, the first phenomenon refers to the reaction of main field with the armature field. Okay, because you have main field established by the magnetic poles, north and south poles, right? So that is called as main field. And you also have a magnetic field created by the armature conductors. So what happens in a DC generator is that the interaction of main field and the armature field give rise to a concept called armature reaction. Armature reaction. Okay. So due to armature reaction, what happens is that the flux phi is slightly reduced. So these are all slightly complex concepts. Okay, so in detail we don't have to deal with, but yeah, I have to introduce you to armature reaction. Okay, so armature reaction is nothing but a phenomenon which happens due to the interaction of main field with armature field, and as an effect of which the flux phi is slightly reduced. If phi is reduced, what happens to EMF? EMF will be reduced because EMF is proportional to flux, right? So, due to the armature reaction, the induced EMF EG is slightly reduced. So, that is the reason the corresponding drop is called as armature reaction drop, ARD. ARD, because armature reaction is contributing in the reduction of voltage. Hence, it is considered as a drop, just like your resistance drop. For example, IARA is your resistance drop, which is actually, reducing the induced voltage, right? Fine. So that is your first drop, ARD. And the second voltage drop is due to the brushes. You have carbon brushes meant for collecting the DC current from commutator, right? So carbon brushes will have a very small resistance value. So it is a standard practice to consider 2 volt. Sorry, yeah, it is standard practice to consider the voltage drop as 1 volt per brush. Okay. And it is also written as BCD. BCD stands for brush contact drop. So by considering the armature reaction drop ARD, and the brush contact drop BCD, you can write the induced EMF expression EG as EG minus IAR. This remains the same. This will not change. Minus VT. And you have to include the two drops. You can say minus ARD minus BCD equal to 0. Equal to 0. All right. Or the voltage which is actually coming across the load is VT is equal to EG minus IARA minus ARD minus VCD. So the terminal voltage which is actually appearing across the load is actually less than the generated voltage. Why it is less than generated voltage? Because of all these drops: resistance drop, reaction drop, and brush contact drop. All right. So while solving the numericals, okay, if ARD and BCD is given, you account it. If it is not given, you can assume it as 0. All right. This is the actual expression. All right. So you don't have to explain armature reaction and brush contact drop. What you can do is apply KVL and write this equation, that is EG minus IARA minus VT is equal to 0. Then you can simply say that a practical DC generator will have armature reaction drop, and also it will have brush contact drop. Considering these two drops, we can write the final expression for EMF induced as EG minus IARA minus VT, and include these two drops, that is minus ARD and minus BCD. Okay, so this is what you are supposed to write. And if you rearrange the equation, you can get an expression for the terminal voltage. So terminal voltage is nothing but the generated voltage minus different drops. All right, so that is your equivalent circuit for separately excited DC generator and the corresponding electrical equations. Right. Hope you have understood the concept of equivalent circuit and how to write electrical equations from an equivalent circuit. All right. So what we have done so far, we have completed only one particular equivalent circuit. Right. So in the next class, let us look at the equivalent circuits of a self-excited DC generator. All right. If you have any doubts, you can message me. All right. So I'll stop for today. Thank you so much.